This is an S1 section B question. In this question, we've got Yasmin who's got 5 coins, but the coins are not all the same. One of the coins is biased, and it's more likely to show heads than tails. The probability of heads is 0.6. The other 4 coins are all fair, and she tosses all 5 coins once and records the number of heads. So we'll be having these 5 coins. I'm going to picture the one that's biased as a 50p coin, just so it's a different shape, so we can tell it's a little bit different. And we're going to be interested in finding the probability that x is 0 and the probability that x is 1. The number of heads is x, so we're just looking at having no heads or 1 head. Later on, we'll go on to look at the probability distribution. We'll be drawing a vertical line chart, looking at skewness, expectation and variance, and finally another question on probability. So there's quite a lot involved in this whole question, but as a section B question, it's worth a quarter of the whole paper. So for the first part of the question, we're looking for the probability of getting no heads. Another way of saying that is that all of the coins will come up tails. So the biased coin had a probability of 0.6 of being heads, so 1 minus 0.6, that's 0.4, is the probability of the biased coin being tails. All the other coins are fair, so they have a probability of 0.5 of being tails, and we're multiplying because we want tails and tails and tails and so on, so that's 0.5 multiplied by itself 4 times, which we can write as 0.5 to the power of 4. If we multiply this out, we get 0.025, which is the value that we were given in the question. So then moving on to part 2, and we're looking for the probability that x equals 1. So that means that we want one of the coins to be tails. So it could be, that's one of the coins is heads. It could be that the biased coin is heads and the other 4 are tails. So for the biased coin to be heads, that's 0.6, and for the other 4 to be tails, just like before, that's 0.5 to the power of 4. But there's another situation as well. Or, so we're going to add, the other situation would be that the biased coin is tails and one of the other 4 coins is heads. So for the biased coin to be tails, that's 0.4. Then we've got one of the others is heads and the other 3 are tails, and there are 4 ways of choosing which of these coins comes up heads. So that's 4C1, which is actually 4. So if we calculate all of this, we can use a calculator. That turns out to be 0.1375. I didn't bother to round this one because it only had 4 digits after the decimal point anyway. We then go on to part 3. We're looking for a vertical line chart here. Should be relatively easy to get these marks. Now there's only actually 2 marks on this question. What I'll need to make sure I do in particular is label the scales. We've got the probability and the R values. I could probably have written probability x equals R, which would be slightly better on this axis. I didn't have to put this 0 here. I could actually put the 0 here so that we could see this bar more clearly. What the examiners were looking for in the mark scheme in terms of the heights of these bars was that the last bar was taller than the first one, the bar for x equals 4 was taller than the bar for x equals 1, and the bar for x equals 3 was taller than the bar for x equals 2. Then we're asked to comment on the shape of distribution. Now, you could be forgiven for thinking it looks fairly symmetrical, but that would only have been the case if all the coins were fair. But since we had that biased coin in there, we're actually slightly more likely to get heads than we would be otherwise. So the data has shifted slightly with higher values at the bigger end of the data, so the tail is towards the small end of the data. And skewnesses are named after the direction of the tail, so that's a negative skew, very slightly negative skew on that data. So on to part 5, and we're looking for the expectation and variance of x. This is a nice, easy way to get marks, provided you know the formulae. So the formula for the expectation of x is simply the sum of r multiplied by the probability that x equals r. All that means is that we multiply each r value with its probability, and then we add up all these products. So, as I said, it should be straightforward. So we've got 0 multiplied by 0.025, and then we've got 1 multiplied by 0.1375, and so on. We add up all of these to get our final answer, which in this case gives us that the mean is 2.6. We can check to see if that looks sensible. So on average, we'd expect, well, if the coins were fair, we'd expect about 2.5 heads, but we've got that biased coin, so it's slightly more likely. So a mean of 2.6 heads seems sensible. Notice that I've used mu here to represent the mean. That's just a Greek letter M, and M for mean seems sensible, and that's the one we use in the formula. So the expected value of x is mu, which is 2.6. Moving on to the variance, the formula for the variance is very similar, but instead of just doing r multiplied by the probabilities, we use r squared. So it would be 0 squared times the probability of getting 0, 1 squared times this probability, 2 squared times this probability, and so on until we get 25 times the last probability. And that's not the whole formula though. We have to remember to subtract mu squared. So we're going to subtract 2.6 squared from this value. So I typed that into my calculator and I got the sum of r squared times the probabilities was 8, and I subtracted 2.6 squared to give me a value of the variance of x, which is 1.24. So that's how much the number of heads varies by. There's actually a slightly quicker way to calculate this in practice using the stats mode on your calculator. If you like, completely ignore this section and go on to the last part of the question. But if this is not going to confuse you too much, you might find this a slightly quicker thing to do. So, what's going on here? I've got the same working written down from before. I'm just going to show another way that we could get these values. What I would do is to type the data into the calculator in stats mode. Now, if I go to stats mode on my calculator, I might not have this frequency column here. So what I need to do is to press Shift and then the mode button, and then it doesn't look like the menu is going to help me. I actually press the down arrow on the calculator, and then it will come up with stats as one of the options. It will then ask me if I want frequency on or off, and I'll ask for frequency on. And then I press the mode button again, and then I'll click on stats, and then this time I'll click on one variable and it will have a column for frequency ready to enter the data. Now the reason I'm doing this is because I want to add up each R value by the probability. Now if I put the R values in the X column and the frequencies, I'm going to use the probabilities, then the sum of X will actually do the sum of X times the frequencies, which will in fact be the sum of R times the probabilities. So a quick way to calculate this value multiplied by this one plus this times this and so on is to simply put the values in the calculator. But then the mean, it's not going to be X bar, it's just sum of X, because what I want is this sum of the products. So sum of X will be 2.6. The really handy thing with doing this is that I can then use sum of X squared, because in this context, what sum of X squared will actually give me will be the R values squared multiplied by the probabilities. So sum of X squared is in fact this first term, sum of R squared multiplied by the probabilities, and then I can just simply get that value and subtract mu squared. So that's a much quicker way of doing the calculation. And finally, we're on to part 6. This is probably the most confusing part of the question, so we need to think very carefully and keep a clear head while we're doing it. So, Yasmin's going to toss the 5 coins 3 times, and we want to find the probability that the total number of heads is 3. Well, there's lots of ways this could happen. For example, if she does the first toss and she gets, let's say, 2 heads, and then perhaps on the second toss she gets 1 head, then that's her 3 heads, so in the third toss she'd have to have no heads. Or perhaps she'll get all 3 heads in the first 5 coins, or perhaps there'll be 1 head within each set of 5. There's lots of different ways of doing it, so we should list all the possible outcomes. So, we could have one head in each section. We could have two heads, and then from one set, one head from another, and no heads from the third. That's the scenario I've indicated up here. Or we could have all three heads in one of the tosses, and then no heads in the other two. So there's a few things we need to be careful of here. To get one head in each, we've already worked out previously in the question, or from the table that we were given for the discrete random variables, we know the probability that x equals 1 is 0.1375. So to get 1 and then 1 again and then 1 again, that's just going to be the probability that x equals 1 cubed. And there's just one way of doing that. On to the slightly harder ones. Well, if we get 2 heads, 1 head and 0 heads, that would be, it could be the first set that gets 2, the second that gets 1, the third that gets 0, and we'd multiply those three probabilities using the values from the table, but it could be in any order. Perhaps it will go 1, then 2, then 0, or 0, then 1, then 2, and so on. There are 3 factorial ways of doing this. So we need 3 factorial, which is 6, multiplied by the probabilities of getting 2, 1, and 0 heads. These are the values taken from the discrete random variable table. And finally, we've got the case where we have 3 heads in one set and then no heads in the other 2. So again, it could be the first one that's 3 and the other 2 are both not, or it could be the second one or the third one that gives us all 3 heads. So that's 3 ways of doing that. So it's 3 ways of getting 3 heads, its probability from the table, multiplied by 0 heads, its probability from the table squared. So typing that carefully into the calculator, we end up with a value which, as standard, I would round to 3 significant figures. So that's 0.00940 to 3 significant figures.